cities are a testament to some of the greatest accomplishments of human civilization. Feats of engineering that dazzle with millions of lights. But the bright lights conceal something even more amazing. Turn them off, and behold, a great city in the sky.
What is this? Well, this is the Milky Way. This is our galaxy. Well, if you'd like, you can think of the galaxy as a city of stars.
Our sun is just one of the 200 billion stars that make up a vast cosmic city. A city we're just beginning to know.
It's really a wonderful time to be an astronomer. Especially in studies of the Milky Way, we're undergoing something of a revolution. In fact, we can take you places that are really quite remarkable.
We're about to make a major move. We're picking up the Earth and traveling across thousands of light years, relocating to distant neighborhoods of the galaxy. From our new address, the sky looks different, full of wonder and beauty, lit by a multitude of brilliant suns. Revealing the power of stars that lived billions of years ago. Out here, we'll get a glimpse of the future when our sun exists no more. It's a journey to unravel some of the greatest mysteries of the universe. How the Milky Way was born, how it survived for so long, and how it will eventually die. But before our trip can begin, we need a map of where we're headed. And making one is the job of astronomers like Robert Kirshner and James Bullock. The first obstacle is simply figuring out what kind of galaxy the Milky Way is. The Hubble Space Telescope gives astronomers the capability to see billions of other galaxies. Each one is different, but it turns out there is a pattern.
When we look out to study other galaxies in the universe, we see that there are basically two types of galaxies.
The first type, elliptical galaxies, appear as large balls of stars. And no matter what angle they're viewed from, they always look rounded. The other main class is the so-called spiral galaxies, because their stars are contained in arms that spiral out from their centers. From a distance, a spiral galaxy looks something like a frisbee. The key to correctly identifying the Milky Way is written across our night sky.
The Milky Way, we believe, is a spiral galaxy. So what we're really seeing when we look up at night at this band is we're seeing our place in the universe. We're part of a giant disk of stars.
But that's just an insider's view.
Now, of course, I can't show you a picture of the galaxy in all its glory. We can't fly above the galaxy and take a picture of it and show you. We're stuck in the disk of the galaxy, but we can still image it from the ground. In fact, this image is a picture of our galaxy, the Milky Way, taken from Earth.
This is one of the most detailed images of our galaxy ever created. It's made from 800 million pixels contained in over 1,000 individual photographs taken from the darkest places on Earth. The photos have been painstakingly stitched together to create this breathtaking view. But impressive as it is, it's only part of the picture.
It's something like a pizza, and if you were in the pizza, if you were a pepperoni, your view would not be a very clear one of what the whole story was. In the same way, we don't see the whole reach of the Milky Way.
What astronomers really need is a bird's eye view.
You would need to get out of the Milky Way to really see what it looks like. We don't have a way to do that, but we can look at other galaxies and see what they look like.
Hubble's cameras capture nearby galaxies in amazing detail, like Messier 74. Although it's over 30 million light years away, it's one of our closest neighbors. Messier 74 is a beautiful spiral galaxy. Its large, starry arms sweep out from a bright core.
This is an example of a galaxy that astronomers think looks a lot like our galaxy, the Milky Way. This is a great representation of our own star city. In the central region, we have the downtown. This is the bulge, this bright spot in the middle. And from that, we see spiraling out these arms, these beautiful spiral structures we see in this galaxy.
Astronomers compare Hubble's incredibly detailed images of other spiral galaxies with the best images of our own galaxy taken from the ground. Using satellites to measure the distance and density of stars in different directions, astronomers reveal the grand plan underlying our star city. At its heart, a bright central region, the galactic core. Our galaxy's downtown district. From here, two majestic spiral arms, bright bands of billions of stars sweep out. Scutum Centaurus and the Perseus arm. There are also three smaller arms. From one end to the other, our galaxy measures a staggering 600,000 trillion miles.
It takes light 100,000 years to cross our galaxy. This is a big galaxy, and it's quite amazing, if you think about it, that we understand as much as we do about this system.
Our sun and the solar system are located here, in a quiet neighborhood nestled between two spiral arms. This is the galactic home address that we know so well. But our surrounding neighborhoods are wildly different. Like any large city, there are dynamic industrial zones, where heat and pressure forge new stars and others die in violent explosions. Downtown, in the very heart of the galaxy, stars jostle for space, pulled by mysterious forces. Our galaxy also has quaint, historic neighborhoods that tell the story of how our star city was founded. Now, we head to one of the most spectacular locations in the Milky Way. A place that holds the clue to how the 200 billion stars of the galaxy were first created. And it's just around the corner. We're picking up and leaving home. We're taking our planet on a journey. The destination? A place where stars are born. It may look close by, but even traveling at the speed of light, 186,000 miles a second, the trip takes 1,500 years. We arrive at a vast glowing cloud of gas and dust, the Great Orion Nebula. Beautiful new colors fill our evening sky. But this cloud isn't just a work of art. It holds the key to how our sun and every star in the galaxy came to be. The Milky Way is filled with billions of stars in every direction. From Earth, the naked eye also picks out large, dark, seemingly starless patches. To astronomer James Bullock, in these areas, there's more than meets the eye.
Perhaps the most beautiful part of this image is that we have this contrast of dark and light regions running through the plane of the disk. What that really is, it's dust. There are clouds of dust that are casting a shadow from the back of the stars. So the stars are trying to shine their light through. There are dust clouds there that are blocking the light, much like a cloud on Earth would block the sun.
These vast clouds of cosmic gas and dust stretch thousands of light years across the Milky Way. Hubble finds them in most spiral galaxies. Dark, ghostly bands woven through the spiral arms and spreading across the entire disk. But there's something strange about this gas and dust. Sometimes it glows. These bright glowing clouds are called nebulas. Each one is unique and breathtakingly beautiful. The Eagle Nebula, with towering pillars up to 4 light years in size. And the Carina Nebula, with its distinctive green glow. These vibrant colors reveal what gases nebulas are made of.
So for example, if there's oxygen gas, you get a green glow. If there's hydrogen gas, you get a red glow. So analyzing the light from a nebula turns out to be very instructive. It tells us what's there, it tells us what the physical conditions are. We can tell how dense it is, how hot it is, and what it's made of. We can find out a lot about the neighborhood by looking at these clues that come directly from the glowing gas.
The gases glow at thousands of degrees, heated from a mysterious source hidden deep within the nebulas. To figure out what the source is, we need to peer deep inside.
But of course, the gas and dust is in the way. So it's not so easy. It's a very mysterious part of the galaxy. It's a place that we have to use these special tricks to look into.
And Kimberly Weaver is an astrophysicist who's got a few tricks up her sleeve.
I've got a really neat way to show you this. This is a bag that you can't see through with your eye, so a normal telescope that looks at optical light could not see through this. In infrared light, a telescope can see through it. The infrared camera, if I put my hand inside, can see my hand. I'll wiggle my fingers to show you that you're seeing the heat from my hand inside the bag. And this is just like a star that's hidden inside a cloud of gas and dust that infrared astronomers can detect by using an infrared telescope. This is a picture of the Orion Nebula in visible light. We can see all of the gas here located in front of what we know are stars in the background. And we want to be able to look inside this nebula and see the stars. In infrared light, in this image, we can now pick out the stars inside the nebula. And we can see dusty cocoons around the stars.
But scientists still need a way to strip away the remaining dust.
How do we get rid of all this haze and fog? The way to do that is with an X-ray picture. Now when we transition into the X-ray image, you can see just the stars themselves. The X-rays coming from the surfaces of the stars. And now we can study them in great detail.
By analyzing the light from these stars, astronomers make an astounding discovery. Hidden within the Orion Nebula are some of the youngest stars ever found. Stars just a few 100,000 years old, a mere heartbeat in the life of the galaxy. And it's not just the Orion Nebula. Nebulas house baby stars in every spiral arm of the galaxy.
These regions are the nurseries for new stars. There are young stars in these regions that are heating up gas clouds that surround them and making those gas clouds glow pink.
Stars are made out of gas, basically, and our galaxy has gas. In fact, our galaxy, you can think of it as having an atmosphere of gas and dust that surrounds all of the stars that we see in the disk. And it's from this gas that new stars are born.
By observing nebulas at different stages in their evolution, the story of a star's birth begins to emerge. It all starts inside a cold, dark cloud of dust and hydrogen gas, where a quiet tug of war begins. The cloud wants to dissipate, like smoke in the air, but gravity wants to pull it together.
They're in a kind of balance between gravity pulling in and gas pressure pushing back out. Gravity wins, and the material crunches down into a disk that is the beginning of becoming a star.
As gravity pulls more and more gas towards the center of the disk, it gets denser and denser and hotter and hotter. Until finally, at 18 million degrees, a miraculous transformation takes place. Hydrogen atoms fuse together to form helium, and with a burst of nuclear energy, a star begins to shine.
These stars eventually get their nuclear fires going in the core, and when they do, they heat up. They can expel the material that's around them so that it kind of clears up the neighborhood.
Over the next few million years, winds blow the surrounding gas into spectacular swirling patterns.
It blows away the gas, it blows away the dust, and it lets us see this beautiful new thing, this place where the star has been born.
A human lifetime is too short to witness the wonder of a star's birth in the spiral arms. But by speeding up millions of years of cosmic time into just a few seconds, we can see one star born after another. Here and there are even more brilliant flashes of light, coming from some of the most violent and dangerous neighborhoods in the entire Milky Way galaxy. Here, stars aren't born, they die. We're taking the Earth from the familiar neighborhood of the Sun to visit the wonders of the Perseus Arm, nearly 6,500 light-years away. Here lies one of the galaxy's most beautiful sights, the Crab Nebula. Although it's made of gas and dust, this nebula hasn't created stars yet. But for Alex Filipenko, this area does represent the industrial zone of our galaxy, where the building blocks of Earth were manufactured long ago.
Look at that molten iron. Holy moly. The Crab Nebula is a fascinating object. We see these very rapidly expanding gases.
The crab may look static, but gases are racing out from its center at over 3 million miles an hour. Put into motion by a phenomenally powerful and violent event in the past.
When we examine the gases of the Crab Nebula, which are expanding outward, and we extrapolate that expansion backward in time, we find that all of the gases were at a common point about 1,000 years ago.
Back on Earth, 1,000 years ago, early civilizations watched the heavens. In 1054, Chinese manuscripts describe the sudden arrival of a brilliant new star. It shines brighter than any other star, so brightly it's visible during the day. But then, it mysteriously disappears. Today, the Crab Nebula lies in exactly the same part of the sky where the Chinese observed their brilliant star. What they witnessed was the moment the crab was born.
The Crab Nebula was produced by the colossal, titanic explosion of a star at the end of its life. It's a supernova remnant.
The spiral arms of our Milky Way are littered with these colorful remnants. Tombstones of stars that died violently in cataclysmic explosions called supernovas. To figure out this mystery, astronomers need to locate the next victim, a massive star at the brink of death.
Astronomers are like detectives. We have to figure out what's going on in the universe, sometimes based on a minimal number of clues. And in the case of most astronomers, the clues come from only the light.
Andy Howell knows catching light from a supernova is all about timing.
Supernovae happen about once every 70 years in a galaxy on average, so about the human lifetime. So chances are you're not going to see one in your lifetime. In fact, the last one in our galaxy that anybody saw was about 400 years ago. So it's been a long time, and I study supernovae for a living. I couldn't do this if I had to just wait for one in our galaxy.
But thankfully for Howell and Filipenko, there's no shortage of galaxies.
So what we do is we look at other galaxies, more distant galaxies. There are billions of galaxies out there, and we see the supernovae that happen in those galaxies. And if you look at 70 galaxies, on average you'll find one a year. If you look at 700 galaxies, you'll find 10 a year, and so on.
There's power in numbers. If we look at thousands of galaxies, we improve our odds tremendously.
This is a supernova that Filipinko and his colleagues are lucky enough to catch. An exploding star on the outskirts of a galaxy 55 million light years away. It briefly outshines the entire galaxy. The light of 1 billion suns distilled into one dying star.
It takes supernova light 1 million or even 1 billion years to get here. They're millions or billions of light years away, but they only shine for about a month. So we have this little tiny window to study these things before that light is gone forever.
In the workshop, Howell and his team are busy preparing their telescopes.
Pretty cool.
Oh, that's great.
We're building a network of telescopes so that we can study supernovae in greater numbers, in greater detail than we've ever been able to before. Let me show you the telescopes we're building. These are the 0.4 meter telescopes, and there are 4 of them here, and we're building them, 20 of them in total, and putting them all around the world. So some of these first ones will go to Chile. We have some in Hawaii already. So let me show you one of the bigger telescopes we're building here. Here we have the 1 meter telescope. We're building about 15. The mirror's not here yet, but this is where it's gonna go. That will reflect the light we gather from the supernova. We have to be able to point anywhere in the sky. And so you can see that the telescope pivots along this axis and the C-ring moves. The great thing about this kind of observing is that it's totally robotic, and I can just sit here in Santa Barbara and have a beer and pizza while the telescopes do their work. All new discoveries about supernovae from all different places in the universe.
Once they've caught the light of a dying star, the detective work begins.
We collect that light and we analyze it in great detail in order to determine what's going on. What's the chemical makeup of the star? What's the pressure inside? What's the temperature? What kind of nuclear reactions are going on? How does a star explode? All of these things we figured out through the analysis of light.
Astronomers deduce that only stars with a huge mass go out with a bang.
A massive star has a very interesting and vigorous life. Initially, it fuses hydrogen to form helium, and that produces energy. That makes the star shine. Then the ashes of that reaction, the helium, fuse together to form carbon and oxygen, releasing yet more energy. Then the carbon and oxygen can fuse into still heavier elements, magnesium and sodium and neon and things like that. And then silicon and sulfur, and finally iron.
When it starts to make iron, the giant star is doomed. In the core, a fierce battle takes place. Energy pushes outwards, holding it up, while gravity wants to crush it inwards. The battle continues as the star makes heavier and heavier elements, producing energy while fending off total collapse. But once it starts to form iron, the battle is lost.
Fusion of iron nuclei into heavier things does not release energy, it absorbs energy. So an iron core builds up, but finally it becomes so massive that gravity wins. The iron core collapses. In less than a second, the outer layers collapse inward, then rebound and get blown to smithereens.
from this death comes new life.
We're at a foundry here, and they're pouring molten iron from old machinery. And they're going to make parts for new machines out of that iron. So they're recycling it. But all that iron was created and ejected into the cosmos by gigantic stars that exploded as supernovae. Those explosions created the iron, ejected it into the cosmos, and then it got incorporated into planetary systems like ours. But ultimately, the atoms of iron were created by exploding stars.
Supernovas are the industrial zones of our star city. Cosmic foundries that forge new elements. In catastrophic explosions, heavy elements are spewed out into our galaxy, enriching it over billions of years.
So if some stars were not to explode in the industrial zones of galaxies like our Milky Way, then we wouldn't have these industrial zones here on Earth. It all is linked. We're all linked to the cosmos.
Our lives today are only possible because of events that happened thousands of millions of years ago in the hearts of supernovas.
It's fascinating to realize that the heavy elements in our bodies, the carbon in our cells, the calcium in our bones, the oxygen that we breathe, the iron in our red blood cells, all of those heavy elements were synthesized, created through nuclear reactions in stars, and ejected into the cosmos by supernovae.
But only a handful of stars are massive enough to die as supernovas. Most stars, like our Sun, suffer a more gentle death.
Most stars don't die in a cataclysmic explosion. Our own Sun, for example, a typical star, will die with a whimper, not a bang.
Death comes when the gravity pulling in finally succumbs to the nuclear energy pushing out. When this happens, any star, even our Sun, will die.
In about 4 or 5 billion years, it'll grow into a much bigger star, a star called a red giant. And the outer atmosphere of gases will be held so loosely by the Sun at that time that the gases will be blown away gently in what I call a cosmic burp.
These cosmic burps leave behind dying stars that litter the spiral arms as they slowly shed layers of elements.
Some layers are oxygen, and some layers are silicon, and some layers are sulfur. And those are the different colors we see in the Hubble Space Telescope images.
Not far from our Sun is a place where a star is dying. The Helix Nebula. It sheds light on how most stars end their lives. Our Sun is destined to follow a similar path when it dies, 5 billion years from now. But in other neighborhoods in the galaxy, stars suffer a fate worse than death. At the center of the galaxy lies a place where stars disappear altogether. We're taking the Earth from the safety of home to go downtown to the heart of the Milky Way. It's a dynamic, exciting district, but it's also a risky place to hang out. Andrea Ghez has spent over 15 years exploring this neighborhood.
If we were to take a trip from the spiral arms out where we are by the sun down to the center of the galaxy, it would be an interesting trip. It would be very much like moving from the suburbs into the heart of a very busy metropolitan area.
As we head downtown, the number of stars increases.
So the density of stars is tremendous at the center of the galaxy. It's about 1 billion times higher than out here by the sun.
Here at the center of the galaxy, there are so many stars in the sky that the Earth is bathed in perpetual light. It's a stunning but dangerous sight to behold. The stars aren't just close together. They're moving at super speed.
Going to the heart of the galaxy might not be dissimilar to going to an amusement park. The rides are somewhat similar to how the stars orbit the center of the galaxy. 10 million miles per hour compared to, say, our sun is about a factor of 50 times faster. So something has to be going on at the center of our galaxy to make that happen.
But figuring out what is no small task. The heart of our galaxy lies 26,000 light years away. It's difficult to observe through the vast amounts of stars, gas, and dust. And there's another problem even closer to home: the Earth's atmosphere.
The atmosphere is great for us. It allows us to survive here on Earth, but is an absolute headache for astronomers. It's very much like the problem of looking at a pebble at the bottom of a stream. The water in the stream is moving by and it's turbulent and it makes it very difficult to get a clear vision. In the same way, looking through the Earth's atmosphere prevents us from getting clear pictures of the stars at the center of the galaxy.
So astronomers like Ghez turn to a technique called adaptive optics to get a better view. By measuring how a laser beam is distorted in moving air, it's possible to compensate for the atmosphere's blurring effect.
So let me show you an example of how powerful adaptive optics is. The stars that we want to see are the ones that are at the very center. We think the heart of the galaxy is right within the center of this box, which is panned out here. Without adaptive optics, this region looks completely blurry. You don't see the individual stars. With adaptive optics, you see the individual stars.
For 15 years, Ghez has taken infrared images of the stars at the heart of the galaxy to produce an extraordinary time-lapse movie.
So if we zoom into the very heart of the galaxy, we can actually see the data that we've taken over the last 15 years, and you can see the stars, and you can see the tremendous motion that they've gone through. In particular, SO2, which is my favorite star. Every astronomer has a favorite one. So you can see SO2 goes around, and in particular, you can see as it gets to the center of the frame, it moves much more quickly. So something's interesting as it goes through that region. So putting everything together, all the measurements that we've made, we've been able to make an animation that shows how the stars have moved over the course of 15 years. Each star goes whipping around the center of the galaxy. In particular, the most striking thing that you'll notice is the motion of SO2. So SO2 goes on an incredible roller coaster ride. It comes whipping around and then back out.
For an object to have enough gravitational pull to send SO2 on rapid orbit around the center of the galaxy, it must also have a huge mass.
SO2 goes around once every 15 years, and what it tells us is that there is 4 million times the mass of the Sun confined within its orbit.
Astronomers know of only one contender that has a giant mass but is so small.
So that's an incredible amount of mass inside a very small volume, and that's the key to proving a black hole.
And so, at the center of our galaxy lies a massive black hole, an object whose gravity is so strong, not even light can escape it. This is a real image of the center of our galaxy. We can't see the black hole, but we can see bright clouds of dust and gas spiraling toward it. We're nearing the black hole. It's at the center of a stream of dust and gas. The debris of stars blown apart after straying too close.
Black holes grow with time, and that happens by material falling onto it, accreting onto it. And that material can come in the form of either gas or stars that get torn apart by the black hole itself.
At the center is the invisible black hole. This is the material it feeds on. The glowing region is the accretion disk. Here, star debris falls inward and whips around at astonishing speed. Friction heats the debris up to such high temperatures that it glows white hot.
So at the center of our galaxy, we do have a black hole. We now know that today, but it's not producing a tremendous amount of energy. So it's perhaps, we could say, it's a black hole that's on a diet. It simply doesn't have a lot of material to feast on.
But what would happen if SO2 and the other stars were pulled inward by the black hole?
What happens when that material falls onto the black hole is that the black hole, there's radiation associated with the black hole, and it can generate these jets squirting out from the center of the galaxy.
Spewing out subatomic particles close to the speed of light, the beams are like vast cosmic searchlights. This is Messier 87, a large elliptical galaxy that has a supermassive black hole at its heart. It's feasting on its own stars. Shooting out from its bright core are jets that travel over 5,000 light years.
I like to call these the prima donnas of the galaxy world. These are the 10% of galaxies that are show-offs.
Astronomers believe that the massive black hole at the heart of the Milky Way has been there from the very start. But in order to get back to where the galaxy first began, we have to travel out to the oldest neighborhood in our star city. We're traveling upward, away from our solar system, out of the spiral arms of our Milky Way. Up ahead lie vast clusters of stars that orbit the heart of our star city. There are over 150 of them. These satellite towns, called globular clusters, hold the answer to one of the greatest mysteries in astronomy: the true age of our galaxy.
Globular clusters are really fascinating groups of stars. They contain about 1 million stars each. And the thing that's really cool about them is the stars are really tightly packed.
If you could visit a globular cluster, the night sky would be spectacular, where many of the stars would be as bright as the full moon.
And the nighttime sky in all directions would be filled with bright nearby stars. It would be like fireworks all the time.
Besides the sheer number of stars, there's something even more intriguing about these clusters.
One of the very interesting aspects of globular clusters is there's no sign of young stars.
Stars are like people. Look at them and you can guess their age and the lives they've led. With people, gray hairs and wrinkles are the telltale signs. With stars, it's color and size.
So the biggest stars, the most massive stars, the ones with the most gas, live life in the fast lane. They live very short amounts of time, but they burn very brightly, and they're very, very hot, and so they tend to be blue.
On the other hand, you have the red stars, which use their energy very conservatively, last for a long time, don't glow too brightly, and those stars last for a very long time.
So by measuring the brightnesses and the colors of the stars in a globular cluster, we can figure out how old they are. And here's the remarkable thing. They're very old. Globular clusters, at least the stars in globular clusters, in many cases are almost as old as the universe itself.
Globular clusters are living fossils. They're like discovering a community of people who've been around since the Stone Age. Some stars here have been shining for 12 billion years, more than twice as long as the sun. And that's a helpful tool in placing an age on the Milky Way.
Globular clusters are part of our galaxy. They orbit our galaxy. In some sense, they're tracers of our galaxy itself. And so by the fact that the globular clusters are so old, it suggests that the galaxy is old.
And our galaxy isn't just old, it's very old. In fact, the Milky Way is one of the oldest objects in the cosmos. It's been around almost since the beginning of the entire universe, at least 12 billion years. Globular clusters also show that the chemistry of the galaxy back then was very different from how it is today.
We can measure the chemical properties of those stars. Turns out they have very low abundances of the heavy elements. Things like iron are very rare in globular cluster stars compared to a star like the Sun.
That means the early galaxy was a far less colorful place. Without heavy elements, there weren't the beautiful hues we see in nebulas and supernova remnants today. Even more importantly, it was a galaxy without life. It took billions of years for stars to form enough heavy elements for the evolution of life to begin anywhere in the Milky Way. Leaving many to wonder how the galaxy has managed to keep going for so long.
One of the puzzles about our galaxy is that we know that it's had stars forming continuously for about the last 10 billion years. But at the rate it's eating up its gas now, it's forming new stars, it should burn out that gas soon. It should run out of fuel. And so there has to be some source for new fuel.
That source must be outside the galaxy. And recently, astronomers made a startling discovery. Globular clusters aren't the only groups of stars orbiting the Milky Way. There are other tiny galaxies circling our galaxy called ultra-faint dwarf galaxies.
The reason why we haven't known about these dwarf galaxies for very long, these so-called ultra-faint dwarf galaxies, is that they contain just a few hundred stars, 1,000 stars. So you try to find a clump of 1,000 stars while looking through a mass of 1 billion stars. It's not easy. This is a needle in a haystack problem. And it's only because we have the precise maps, it's the precision of modern astronomy that's allowed us to discover these extremely interesting dwarf galaxies.
These elusive bodies may help solve the mystery of what's fueling the galaxy.
So these dwarf galaxies are whizzing around our galaxy. They're in orbit around it. Now, sometimes they get too close. And when they get too close, they get ripped apart. In fact, they get eaten, in some sense, by our galaxy.
This computer model shows dwarf galaxies as colored disks, with our galaxy in the center. Over time, our galaxy pulls dwarf galaxies in, devours them, and uses their gas and dust to eventually form new stars.
So in much the same way that a large city might sort of cannibalize its neighbors, the Milky Way is cannibalizing its dwarf galaxy population.
Globular clusters and dwarf galaxies provide crucial insight to just how old our galaxy is and how it's managed to survive for so long. These bodies were once thought to mark the Milky Way's city limits, the very outer reaches of our star city. But today, astronomers are rethinking all that. Our galaxy might be bigger than what we can see, spreading out further than we ever imagined. We're picking up our Earth and moving from our quiet suburb to a new neighborhood in the outer spiral arm of our galaxy. Here, we'll uncover the mystery of what holds all the stars in the Milky Way together. From our new address, the night sky looks a little different. The Milky Way is smaller and the sky darker. Here, tens of thousands of light years away from the center of our galaxy, we're still bound by the force of gravity.
Gravity is the force that makes any two objects want to move towards each other.
On Earth, cities are built with iron girders and concrete beams. An invisible scaffold which holds buildings up against the pull of gravity. Without this scaffolding, skyscrapers would crumble and bridges collapse. Gravity governs Earth and the entire universe. Anything that has mass has a gravitational pull. The more the mass, the stronger the pull. With 200 billion stars, the Milky Way has a huge mass and a tremendous gravitational attraction to match. So, like a building, our galaxy also needs propping up against the force of gravity.
Imagine the disk of our galaxy. If you just took a disk of stars and put it there, gravity would tend to make this disk collapse in on itself, and it would immediately just fall together. That's not what we see with the galaxy. What's actually going on is the stars are orbiting around the center, and that's what keeps them from falling in much the same way that the Earth is orbiting around the sun.
The planets in our solar system are in a delicate balance. Gravity pulls them towards the sun, while their orbital velocity wants to fling them out into space. In order to stay balanced, planets further from the sun must orbit more slowly.
If you go to more distant planets at the edge of the solar system, they're going around the sun much more slowly than the Earth is, and that's because the gravity is weaker there.
The same should hold true for stars in the Milky Way. They all orbit the center of the galaxy. But the stars in the outer arm should be traveling more slowly than those closer to the galaxy's heart.
What's interesting is that's not what's going on. The stars in the outer parts of the galaxy are spinning around just as quickly as those in the inner parts.
And they're not the only ones.
It's not just our galaxy, it's every galaxy we look at. Every galaxy we look at seems to be spinning too fast in its outer parts.
These speeding stars should be flung out of the galaxy altogether, but they're not.
That is a puzzle. This means that there's a lot more mass there that we just can't see.
Mass that produces the gravity that holds these stars in their orbits. But when astronomers look for the mass, there appears to be nothing there. Leading cosmologists like Joel Premack to an astounding conclusion.
All of the galaxies, all of the stars and gas and dust and planets and everything else that we can see with our greatest telescopes represent about 0.5% of what's actually out there. The rest is invisible. It's mostly some mysterious substance that we call dark matter.
You can't see dark matter. The reason why you can see normal matter is because light shines on it and reflects off of it. That's how you can see me. Dark matter doesn't work that way. The light goes right through the dark matter. The way we detect dark matter is because it has mass. Anything with mass affects other things via gravity. That's the golden rule of mass. That's what mass does. It tugs on other things because of gravity.
Without dark matter, the Milky Way couldn't exist.
So the galaxy is spinning. The galaxy is spinning fairly rapidly. The reason why it can spin so rapidly is because it has so much dark matter. The dark matter has a lot of mass, and therefore it has a lot of gravity, and that's what keeps the stars whizzing around. If you were to magically take all of the dark matter away from our galaxy, it would fly apart. The stars would just keep going straight, and in a very short amount of time, the galaxy would just be gone.
There'd be just a mess of stuff flying every which way. And that's not just true of our galaxy, it's true of every galaxy and every cluster of galaxies in the universe. They're all held together by this invisible stuff that we call dark matter.
So we need the dark matter. It's the glue that holds galaxies together.
The discovery of dark matter has revolutionized our picture of the Milky Way. The stars of the galaxy represent just a fraction of its mass. The rest is made up of an invisible halo of dark matter, surrounding every single star and every creature in the galaxy.
The stars are just the central region. The halo is at least 10 times bigger and weighs much more than 10 times more than all the stars and gas and dust that we can see. It's that whole structure that's the real Milky Way galaxy. And that's not just true of our galaxy, it's true of every galaxy we've ever studied.
But dark matter does more than simply hold galaxies together. Astronomers now think it binds the Milky Way into an extraordinary structure with billions of other galaxies. A structure that reaches to the very edge of the universe. We've left our home galaxy to take the Earth across billions of light years of space and time.
One of the great things about telescopes is they're time machines. Because light travels at a finite speed, when we look at distant objects, we see them as they were when the light left them.
As astronomers look back over billions of years, they see a universe teeming with galaxies. But these galaxies aren't scattered randomly through space. They cluster along delicate filaments woven in an intricate structure. A vast cosmic web that holds the answer to the birth of galaxies themselves. It's a story shrouded in darkness. Look back far enough, and gradually all the galaxies disappear. We've reached a mysterious period of time, 12.5 billion years ago.
There's this time period that we can't see because nothing's formed yet. It's this epoch that's called the Dark Ages.
During the Dark Ages, the universe was a very different place than the one we live in today. It's filled with dense clouds of hydrogen gas. Just as gas obscures stars in the Milky Way today, these clouds of hydrogen block the view inside the early universe.
It's extremely frustrating because this region, this time period, holds within it, in some sense, the Rosetta Stone of galaxy formation.
But there is one clue to what's happening inside those dense hydrogen clouds. Look back further in time to a moment just 380,000 years after the Big Bang. The universe isn't filled with darkness, but with light. Its faint afterglow is still visible to astronomers today.
In fact, this picture is amazing. This is a picture of the early universe. This is an image of the afterglow of the Big Bang.
The universe is filled with a hot atmosphere of matter and radiation. But already the seeds of change are being sown.
Everywhere we look around us in the universe, we see structure. We see galaxies all over the place. Where do these galaxies come from? There's a big clue to this buried in this picture. If you look closely, you can see that there are red spots and there are blue spots. These red regions are regions where there's basically more stuff. And the blue regions are the regions where there's less stuff.
This image reveals tiny variations in the density of the gas that fills the early universe. Minute ripples that will grow with time.
We think that these ripples, these primordial ripples, are the seeds to all future structure. These ripples eventually grew into what became the first galaxies.
It takes a powerful force to grow something so small into something so big.
It's gravity that amplifies these ripples. And in fact, we need an additional source of gravity to amplify those ripples to form galaxies like we see today. And that additional gravity comes in the form of dark matter.
What happens is that first the dark matter forms the structure. The ordinary matter then follows the dark matter. The ordinary matter is hydrogen and helium at this stage. And the hydrogen and helium fall to the center of the dark matter halos that are forming, and that's going to become the galaxies.
Dark matter may be the missing link between these minute ripples in the early universe and the vast cosmic web that now fills space. But dark matter is invisible. So there's no way to actually see it creating the cosmic web. But the process can be simulated in one of the world's most powerful supercomputers.
Here we are at NASA Ames, the research center where we have the Pleiades supercomputer. Each one of these cabinets contains 512 processors. Let me show you. So that's half a terabyte in each one of these cabinets. There's 110 of these cabinets to make up the entire Pleiades supercomputer. So this is a really big supercomputer. This is NASA's biggest.
The challenge is equally big: to develop a virtual universe from its early beginnings all the way to the present day, to see what role dark matter might have played in shaping the cosmos. If you tried to do this on a home computer, it would take over 680 years.
If we're doing our job right, we can put the pictures into a video, if you like, that shows the whole structure of the universe.
And this is the end result. It's called Bolshoi, an amazing visualization of what the structure of dark matter might look like in the universe today.
So what we're looking at is a region about 200 million light years across, which is actually just a small part of our really big simulation that we call Bolshoi, which is Russian for big. Everything that you see here is actually completely invisible. It's not the visible universe that you're seeing. The bright spots are dark matter. They're the halos of dark matter within which galaxies form. And each one of these little blobs would represent probably one or at most a couple of Milky Way-sized galaxies. And you can see that the galaxies are in long chains, filaments we call them. Basically, all the structure is forming along these filaments of dark matter.
Now comes the real test of success. PREMAC compares the Bolshoi predictions with the actual structure of galaxies scientists see in the universe.
As far as we can tell, these simulated universes that we make in the supercomputers look just like the observed universe. There don't seem to be any discrepancies at all. This is exactly the way we see the galaxies distributed in the observed universe.
The Bolshoi simulations are astounding. They match the pattern of galaxies seen in the cosmos today perfectly. It's persuasive evidence that dark matter has been sculpting the universe for billions of years.
No, I'm really impressed with this, because we stuck our necks way out when we made these first predictions. And they turned out to be right, and they keep turning out to be right. And, you know, this is, of course, great joy for a theorist.
By going back to the beginning of the universe, astronomers have uncovered the origin of the underlying structure of the entire cosmos. But our time travel is far from over. The question of how the first galaxies kindled the very first stars still remains. We're taking the Earth inside the Dark Age, a time over 12.5 billion years ago. The sight is spectacular. Our skies are lit by the first stars of the Milky Way. Their light pierces the hydrogen fog, bathing the Earth in strong ultraviolet energy. These first stars will change the way we see the universe forever. Tom Abel studies the life and death of these early stars.
The beautiful thing is that we now have computers. We program them with the laws of physics. Put in some gravity, hydrodynamics, how gases move around, some of the chemistry. And as we evolve it all together, we gain an intuition of how stars come about. And in the case of the very first stars, this is absolutely crucial.
Abel begins with the basic ingredients available during the Dark Ages: hydrogen, helium, dark matter, and gravity. Using computer models, Abel recreates the lives of these early stars.
Here we see one of the first stars in the universe. It's 100 times as massive as the sun, 1,000,000 times as bright.
The first stars are huge, swollen by the massive amounts of hydrogen gas pulled in by the gravitational force of dark matter.
And so even though they have all this fuel to burn, you'd think they could live for a long time, they run through it so quickly that even after a few million years, they're already dead.
The first stars in our Milky Way are fierce, high-octane stars, burning their hydrogen fuel at tremendous rates, racing through their life cycle.
They like the rock stars. They live fast and die young. They run through that fuel very quickly, and even after just a few million years, they already die.
They die in some of the most violent explosions ever to rock the universe. Gigantic supernovas that shine brilliantly. The energy given off during the life and death of these massive stars leads to a miraculous transformation.
In the first billion years of the universe history, galaxies start to form in a dark hydrogen fog, their light not being able to get to us. But as time progresses and their most massive stars put out ultraviolet radiation, it's that radiation itself that changes the fog around them. And the universe becomes transparent in those regions. These galaxies in here clearing out the fog around them.
The blue voids are where energy from the new stars is clearing the dark hydrogen fog.
But towards 1 billion years after the Big Bang, the entire fog has cleared, and we now see all the galaxies and the dark ages end.
As the hydrogen fog lifts, we get our first glimpse of newborn galaxies, including our very own Milky Way.
This remarkable image is the Hubble Ultra Deep Field. It's the longest exposure that's ever been taken with the Hubble Space Telescope. It's a truly remarkable image, probably the most famous to professional astronomers.
For over 11 days, Hubble pointed at a tiny patch of sky, about the width of a dime, held 75 feet away. Every faint smudge of light is a galaxy. For Richard Ellis, it's a treasure trove.
So much like an archaeologist would piece together history by digging into deeper and deeper layers, so a cosmologist like myself uses this image to look at the history of the universe, how the most distant galaxies, seen as they were a long time ago, evolve and grow to the bigger systems that we see around us today.
This image gives us a sense of the dawn of our Milky Way.
When we look at these early galaxies, they don't resemble the star cities that we see today. They're lumpy, they're irregular, they appear to be interacting with their neighbors, they're physically very, very small. So clearly the universe was very different in those early times.
12 billion years ago, the universe is a much smaller place. It hasn't yet expanded to the size it is today. Our young Milky Way is jostling for room.
So it's very difficult for these early galaxies to establish themselves. These early galaxies are struggling to survive at this very early time.
It's survival of the fittest. The largest galaxies grown bigger by devouring the smallest.
So it's tough for these early systems to form, but clearly they do, and they eventually merge with their neighbors and form the biggest systems that we see today.
These collisions in the early universe created the beautiful spiral galaxy we live in today. And they've never stopped. Astronomers believe there's still one final collision in store for the Milky Way. One that will change it forever. We've transported the Earth 3 billion years into the future. The sky is dominated by a massive galaxy called Andromeda. The view may look peaceful, but one of the greatest calamities in the universe is about to take place. And clues to the impending disaster lie in these mysterious Hubble images. Galaxies unlike any other. Distorted. Deformed. Astronomers rely on computers for help in decoding what these mysterious objects represent.
What we do is we make galaxies that look just like the Milky Way and similar galaxies. And we let them evolve in the computer. They develop the spiral structure. They look quite realistic. We then put them on a collision path.
Freeze frame these simulations and match them with real images, and suddenly the picture becomes clear. It's the greatest clash in the cosmos. Galaxies in collision. Like cities, galaxies tend to cluster. Our Milky Way belongs to a cluster called the Local Group, made up of at least 50 galaxies. The largest in the pack is Andromeda, a spiral galaxy that's even bigger than ours. Today, Andromeda lies 2.5 million light years away. But astronomers like Abraham Loeb believe that distance is closing in.
When I started working in astrophysics, I noticed that most of my colleagues are thinking about other galaxies interacting with each other, colliding with each other, and I was wondering, why aren't they examining the future of the Milky Way and the Andromeda Galaxy as they will come together?
Trouble is brewing for our star city.
Our galaxy is rushing toward the great galaxy in Andromeda. They're rushing toward each other. And they're going to encounter each other in a couple billion years.
Loeb and his colleagues decide to simulate this intergalactic clash of the Titans.
This was the first simulation of its kind. Initially, the two galaxies plunge through each other, producing these beautiful tails of stars due to the force of gravity. They run away, turn around, and come back together to make one big spheroid of stars, which I called the Milkomeda Galaxy.
When the Milky Way merges with Andromeda, almost 1 trillion stars will come together.
The beautiful spiral structure of our Milky Way galaxy is not something that's going to last forever. It's going to be a mess for a while. The collision will not be one in which these two things are destroyed, but it is one where the gas in each system will collide with the gas in the other, that it'll have a burst of star formation.
And the formation of these new stars will mark the rebirth of a new galaxy.
This spectacular Hubble image shows the antenna galaxies, a grand cosmic collision between two spiral star cities. The galaxies are in a frenzy of star birth. A multitude of nebulas glow pink in the darkness. One final flare of stellar activity before the galaxies merge to become one. This is the fate that awaits our Milky Way when it merges with Andromeda 3 billion years from now.
When they collide, there will be a lot of new star formation that takes place. There will be a kind of rejuvenation of the Milky Way for a little while, and then eventually this combined system will settle down to become a new thing, probably a bigger galaxy than either of the galaxies out of which it was made.
But the real surprise is the shape of this new galaxy.
A new galaxy is formed where instead of the disks that the original galaxies had, where all the stars are going around more or less in a plane, instead, the stars are going every which way, just like the elliptical galaxies that we see. And so we're pretty sure that this process must be a large part of how elliptical galaxies form.
The collision of the Milky Way with Andromeda will leave behind a giant elliptical galaxy. But before that happens, there'll be one final sight to behold.
The image of Andromeda will be stretched across the sky, looming as big as the Milky Way itself. And it's conceivable that there would be human beings like ourselves looking at the sky and seeing this spectacular image.
We might not be the only beings enjoying the view. Could our galaxy be home to other civilizations? Unknown life yet to be discovered inside the Milky Way? There are around 200 billion stars in our galaxy. But there's only one neighborhood we know for sure that sustains life. Earth.
The sun powers almost everything here on the Earth. It's the energy source, it's the engine of life and many other processes. And life here on Earth is based heavily on water. And it's liquid water that's the key to life as we know it. And it's because liquid water serves as the solvent, the cocktail mixer for the biochemistry of life.
Earth is the only planet in our solar system with abundant liquid water. As with any prime real estate, it's all about location, location, location.
Venus is closer to the sun, Mars is farther from the sun. And there's a zone in between the blazing hot furnace of Venus, the frigid Mars. That zone in between we call the habitable zone, and the Earth lies smack in that thing, where water would be in liquid form, not in steam, too hot, not in ice form, too cold, but rather a temperature that, as Goldilocks said, is just right for life.
The location of a habitable green zone depends on the star. With hot blue stars, the green zone is further out. With cooler red stars, it's closer in. Every star in the Milky Way has a habitable zone. But not every star has planets within that zone.
In 1995, something happened that was extraordinary. I got a call from my collaborator, Paul Butler, and all he said was, "Jeff, come over here." And it was a moment that I will never forget. I was silent, Paul was silent, and we were just stunned. There on the computer screen, I saw the unmistakable signature of a planet.
Marcy had discovered the first planet around another star. But he couldn't actually see it because the planet was too small and dim.
Any planet orbiting a star is lost in the glare of that host star that outshines it by a factor of 1 billion. And so instead, to detect planets, we watch the stars. And in fact, a star will wobble in space because it's yanked on gravitationally by the planet or planets orbiting that star. And by watching the star alone, we can determine whether the star has planets and how far out those planets are from the host star.
So far, astronomers have found over 400 planets orbiting stars in our galaxy, but none of them seem to be in habitable zones.
One type of giant planet orbits very close to its star. We call them hot Jupiters because these Jupiter-like planets are so close that they're blowtorched by the intense heat from the star. The other sort of planet we've found is also bizarre. We've found planets that orbit in elongated orbits, elliptical, stretched out orbits, but then the planets go very far from the star where they would be quite cold. And so the planets that we've found so far are a little too weird for us to imagine that life would have a good chance of surviving.
Power on. External.
But all that may be about to change. Recently, NASA launched a powerful new telescope called Kepler to hunt for Earth-sized planets that may orbit habitable zones around nearby stars.
Kepler works in the most simple way. All Kepler does is monitor the brightness of 100,000 stars with such exquisite precision that it would detect a planet as small as an Earth-like one as it blocks the starlight.
We see the same thing from Earth when Venus and Mercury are silhouetted against the sun. But Kepler's task is far more difficult.
It's a little bit like having a searchlight in which you're trying to detect any dust on that searchlight by noticing a dimming of the searchlight when one dust particle falls on this massive searchlight.
From this tiny dimming, the size of the planet can be measured. And together with the way it causes its host star to wobble, Marcy can work out its density.
And of course, this is glorious, because by these measurements, we'll be able to distinguish gaseous planets, probably not suitable for life, from the rocky planets that may have a surface covered by liquid water.
Astronomers aren't sure how many planets Kepler will find. But with 200 billion stars in the Milky Way, the odds look promising. Seth Shostak has done the math.
You know, the indications are a lot of those stars have planets, maybe half of them do. And since planets, you know, being like kittens, you don't just get one, you get a couple. They're probably on the order of 1 million planets out there.
1 trillion planets. It's an unimaginably vast number. But what are the chances of them being in a location where life can flourish?
We can expand the idea of a habitable zone around a star to a habitable zone within our entire Milky Way galaxy.
The search for life begins with the search for a galactic habitable zone, the safe haven that allows life to flourish.
In close, at the hub, there's an extraordinary amount of X-rays, harsh radio waves, even gamma rays, that would certainly destroy fragile, single-celled life just getting a start toward evolution.
Downtown is dangerous. There's a supermassive black hole down there. You get too close to that, all sorts of bad things can happen. There are also a lot of stars down there, and a lot of stars sounds good. But on the other hand, if you have too many nearby stars, they tend to shake up all the comets in your solar system. They're constantly pummeling you with these collisions that, just ask the dinosaurs, are not always good for you.
The spiral arms may offer the safest neighborhoods in the galaxy. But even here, danger may lurk around the corner.
If you happen to be on a planet near a supernova, that explosion could ruin your whole day. Life might get started, and then, another couple 100 million years later, it gets wiped out. So these areas are sort of no-go zones, no man's land. Well, no alien's land, perhaps.
The outer reaches of our Milky Way are quieter. But here, life would still find it difficult to take root.
At the outskirts of our Milky Way galaxy, there aren't very many heavy elements of which the cells of our bodies and life as we know it are composed, and so we may not have the essential building blocks of life at the outer edges of our own Milky Way.
So it's not an accident that we are where we are. Our neighborhood, tucked away between two spiral arms, is prime real estate. It's remained relatively unchanged for billions of years, giving life time to establish and evolve. Other advanced civilizations, if they exist, are likely to live in similar neighborhoods, cocooned from the dangers of the galaxy. We haven't found them yet. But then again, our galaxy's a big place.
We haven't found any life elsewhere. We haven't found pond scum. We haven't found dead pond scum anywhere else, not convincingly. And why is that? Well, fewer than 1,000 stars have been looked at carefully for planets that might have intelligent life. So, it's sort of like going to Africa looking for megafauna, elephants, giraffes, something like that. And you land in Africa and you look at the first square yard of real estate there and you say, no elephants here, then you give up. Well, we shouldn't give up. We're just beginning.
If we do find life, it's amazing. If we find life elsewhere in the universe, I think the stock market won't budge one bit. But we humans will know for the first time in human history that we're not alone, that we have kindred spirits out among the stars, and that our destiny may well be to venture to the stars, communicate with them, and become members of a great galactic country club.